History of lithium batteries. Volta battery. Throughout history, different batteries have been created. Voltas from 1800 consisted of stacked metal elements of copper and zinc plates separated from each other by textiles soaked in acid, obtaining up to 1.1 volts. Lead-acid batteries, used in many cars today, produce 2 volts each. 6 are usually placed to produce the usual 12 volts. There are also nickel-iron, nickel-cadmium, nickel-metal hydride batteries, etc. The problem with these batteries is that they contain toxic metals such as lead or cadmium, and that they offer relatively low energy densities. Subscribe to the Fleet Management channel. Your subscription is a great support to continue making new videos. Subscribe, subscribe, subscribe. The higher the energy density, the more energy is available to accumulate or transport per volume or mass. Lead-acid batteries offer 30 watt-hour kilogram of energy density, nickel-iron 40 watt-hour kilogram, nickel-cadmium 50 watt-hour kilogram, and nickel-metal hydride 80 watt-hour kilogram. Lithium-ion batteries offer at least 120 watt-hour kilogram and a voltage of 4.2 volts.
Learn about our fleet management consulting and training services. Reduce costs and optimize fleet management activities. We electrify your fleet of vehicles. We carry out the electrification plan until its implementation, known as
History of the lithium-ion battery. The oil crisis in the 70s began the boom in the lithium battery research career. The perfect anode would have to be lithium. All that remained was to discover the perfect cathode. The first lithium-ion battery had a lithium titanium sulfide cathode that was capable of accommodating the lithium ions arriving from the anode inside. The anode was made of metallic lithium, and the electrolyte was lithium hexafluorophosphate dissolved in propylene carbonate. In this electrolyte, the lithium was protected from both water and air, gaining stability. This achieved 2.5 volts. The first commercial lithium battery was an evolution of this one developed by the Exxon company. It used lithium as the anode, titanium disulfide as the cathode, and lithium perchlorate dissolved in dioxylane as the electrolyte. But there was a problem. When these batteries overheated, they would explode. They discovered that what was happening was that after each charge and discharge cycle, lithium dendrites were formed that crossed the electrolyte barrier until they reached the cathode, thus producing a short circuit. The problem seemed to be solved by using a different cathode. Instead of a metal sulfide, a metal oxide was tested, specifically cobalt dioxide, which combined with lithium is called lithium cobalt oxide. Lithium cobalt oxide has such a high reduction potential that it was not even essential to use pure metallic lithium as an anode, but rather another substance could be used that would accommodate lithium in a more stable and safe way. By using materials without lithium metal, safety over batteries that used lithium metal was dramatically increased. The use of lithium cobalt oxide made it easy to achieve industrial scale production. History of the lithium-ion battery. There are 3 researchers who are the inventors of the lithium-ion battery who won the Nobel Prize in Chemistry in 2019, the German John B. Goodenough, the British M. Stanley Whittingham, and the Japanese Akira Yoshino. Whittingham, who worked for Exxon, led research into the electrointercalation of lithium ions into metal disulfides in the 1970s. Whittingham decided to use lithium not only in the battery anode, but also in the electrolyte, and the results obtained were amazing. While the best batteries of the time ran at 1.3 volts, this new model offered 2.4 volts, and, thanks to the science of collation, it was also rechargeable. Whittingham's battery was not yet known as lithiumion, nor did it use the same chemistry as current ones, but it operated with the same fundamental mechanism, lithium ions inserted into a host electrode. A small button cell version of the battery was made and used in a perpetual solar wristwatch, sold by a Swiss company where it worked perfectly. Despite this successful test, Exxon slowly lost interest in the lithium-titanium disulfide battery. The oil crisis faded, the wristwatch app was considered insignificant, and corporate priorities changed. Finally, the company's managers decided to sell the technology. The battery was licensed to 3 companies, one in Asia, one in Europe, and one in the United States. John Goodenough, who worked for the University of Oxford in the 80s, was the one who proposed the solution to batteries exploding when heated. He solved it with the lithium cobalt oxide cathode and offered an amazing 4 volts. This new version was even better, more energetic and also rechargeable. There was nothing like it on the commercial market, but when Goodenough contacted battery manufacturers in the United Kingdom, the United States and continental Europe, he found no one interested. Oxford University even refused to pay for a patent. To obtain patent protection, Goodenough had to travel to the government laboratory in nearby Harwell, England, and sign over his rights to the invention. This laboratory patented the technology, and it remained inactive. In 1985, Akira Yoshino, in collaboration with the Japanese corporation Asahi Kasei, discovered that petroleum coke was capable of accommodating lithium very efficiently. In many texts it is called graphite, but it is not exactly graphite, but rather a carbon material that has layered graphitic crystalline domains and non-crystalline domains. Lithium ions are accommodated between each other. Years later, however, Harwell's lab received an unexpected call from Sony, the Japanese technology company, to discuss a licensing agreement on a patent that had been gathering dust for 8 years. The call surprised everyone in the laboratory. At first, scientists couldn't imagine which patent had sparked such interest. They soon realized that Sony was citing an old patent titled Electrochemical Cell with Fast Ion Conductors. It was John Goodenough's patent. Sony engineers wanted the patent in order to implement batteries for their new camcorder, called the Handycam. Using the rechargeable lithium cell, it could offer lighter weight and longer working time. His plan was to use Goodenough's cobalt oxide cathode and couple it with a petroleum coke anode developed by Akira Yoshino in Japan for Asahi Chemical in Japan. History of the lithium-ion battery. Sony in 1991, in collaboration with Asahi Kasei, released the first commercial lithium-ion battery with cobalt lithium oxide cathode, anode, and coke anode. The fact that lithium ions enter and exit in an orderly manner at the anode and cathode, forced by the two-dimensional structures of coke and cobalt oxide, guarantees that the batteries hardly have a memory effect. That is, we can charge them without waiting for them to be completely discharged, without fear of the battery becoming corrupted. Sony called it a lithium-ion battery, included it in the Handycam, and offered it to the market starting in 1991. Soon it began to be used in laptops and smartphones. In 1998, Nissan Motor first put a lithium-ion battery in a limited edition electric car called Ultra and began laying out bigger plans. Then, as we know, other automakers followed suit. Neither Whittingham nor Goodenough made any money from their inventions. Goodenough gave up the rights to his lithium cobalt oxide chemistry in 1980, making it impossible for him to make any personal profits. Whittingham's lithium titanium disulfide was used only as a sole application in the wristwatch. In 2019, both scientists were co-winners of the Nobel Prize in Chemistry, along with Akira Yoshino. At that time, 47 years had passed since Whittingham's invention and 39 since Goodenough's development.